In this first concept check question, you're asked to draw the products of the reaction shown. This is a hydroboration oxidation reaction of an internal alkyne, so the product will be a ketone. But in this case, it's an unsymmetrical alkyne, meaning that the two sides of the alkyne are different, so that will lead to the formation of two different ketone products. In this example, the borane can add to the alkene in either direction, placing the BH2 group on the left alkyne carbon or on the right alkyne carbon. And that will give rise to two intermediates that are constitutional isomers. Each intermediate then reacts with hydrogen peroxide and base to replace the BH2 group with an OH. Finally, each enol intermediate then undergoes tautomerization. And remember that the tautomerization reaction will form a carbonyl in the position of the alcohol. So the final reaction products here will be two isomeric ketones, both heptanones, or 7-carbon chains, but one with the ketone in the 3 position and the other with the ketone in the 4 position. Here you're also asked to determine the reaction products. This is a dissolving metal reduction and will generate a transalkene from an alkyne. That means I need to keep the same number of carbons in my starting material and in my product, and then in the product simply convert the alkyne into an alkene, being sure to place the two alkyne substituents, the ethyl and the cyclopentyl groups, in the trans orientation on the alkene. In this last concept check question, you're asked to identify the conditions and reagents that you would use to convert the alkyne given into the alkene shown. And we're told that we'll need to use more than one reaction step. In this kind of question, I like to start by mapping the product onto the starting material to see what bonds form and break and what new pieces might need to be incorporated. And in this structure, I can use the isopropyl group as an anchor that I see is present in both structures. So I'll start by numbering that, and then I see that the alkene carbons originate from the alkyne carbons. So I'll need to reduce the alkyne to an alkene. And the end, the left-hand side of the structure has changed. In the product we have an ethyl group, but in the starting material we have a hydrogen. So that tells me that the first step I might try here is to convert that hydrogen into an ethyl group. And we can do that by first deprotonating the alkyne to make it a good nucleophile. To do that, we use sodium amide. Then the resulting acetylide anion can attack an electrophile. And because I want to add an ethyl group, the electrophile that I'll use here is an ethyl bromide. This reaction will give us the skeleton of the structure that looks like the product. But we have the alkyne and we need the alkene. So the last step here will be to reduce the alkyne to the alkene. And we should also note that the product alkene has a cis stereochemistry. So we have to use reduction conditions that will give us the cis product selectively over the trans. And that's hydrogen with Lindlar's catalyst. So overall, we can convert the alkyne given into the alkene product shown in 3 steps, using first sodium amide, then ethyl bromide to generate the internal alkyne, and finally treating that with hydrogen in the presence of Lindlar's catalyst to give the cis alkene product.